Hey everyone, today we're going to do the second part of 8.3 of bonding theories. And today we're going to focus on something called orbitals. Our key question that we're starting with is how are atomic and molecular orbitals related? Well, first, let's kind of review what we know about atomic orbitals that we learned in chapter 5. Remember, atomic orbitals, there are 4 of them that we learned about. They are s, p, d, and f orbitals. Each orbital can hold a certain amount of electrons. So if we're looking at an s, it has 1 orbital and it can hold 2 electrons. A p, there are a max of 3 orbitals, which can hold 6 electrons. Then there are d, there are 5 orbitals of that, and it can hold 10 electrons. And then f, there are 7 orbitals, which can hold 14 electrons. Today, we're going to expand on that, and we're going to learn about 2 types of molecular orbitals called sigma and pi bonds. And then we're also going to talk about how these atomic orbitals are able to bond with each other and form hybrids. So just as atomic orbitals belong to a particular atom, molecular orbitals belong to a molecule. So for example, H2O has its own molecular orbitals. And when these molecular orbitals actually bind together 2 elements in a covalent bond, we call them bonding orbitals. For example, there is a bonding orbital between the hydrogen and oxygen in H2O. So when 2 atoms combined, it is assumed that the atomic orbitals of each of those elements overlap, and this is what produces our molecular orbitals that we see. It is applied to the entire molecule, and in some ways, atomic orbitals and molecular orbitals are pretty similar. Now, a few things that I want to talk about. In general, covalent bonding usually results in some kind of imbalance between attraction forces and repulsion forces. So remember, the atom is made up of 3 subatomic particles. We've got protons, neutrons, and electrons. Protons and neutrons are located in the nucleus, or we call them nuclei. The nuclei is positively charged because of those protons. Electrons are negatively charged. So if we take 2 atoms that are bonding together, there's a couple things we have to remember. The nucleus of one atom is going to be attracted to the valence electrons of another, because positive and negative attract. However, at the same time, the nucleus that's positive of one atom is going to repel the positive nucleus of another atom, and it's not going to want to be by it because like charges repel one another. Same thing with electrons. The electrons of one atom are actually going to repel the electrons of another atom because here again you have like charges. So why are 2 atoms able to bond and form a molecule if we have things in them repelling each other? Well, that's because the attractive forces are stronger than the repulsion forces. So these molecules are able to bind together through these really strong bonds. There are 2 types of molecular or bonding orbitals we're going to talk about. The first one is sigma, and the second one will be pi. I'm going to talk about each one of their textbook's definition, and then I'm going to give you a way to identify sigma and pi bonds within a molecule. So the textbook definition of a sigma bond is when 2 atomic orbitals combine, they form a molecular orbital that is symmetrical around the axis, and it connects the 2 atomic nuclei together. And the Greek letter for a sigma bond is sigma, which I believe is just a little O with a little line out to the side. So let's illustrate that with a picture. It says 2 atomic orbitals. So here I have an s atomic orbital, and here I have an s atomic orbital. It's like combining hydrogen and hydrogen. What happens is these 2 orbitals fuse and it forms a sigma bonding molecular orbital. So it's like putting 2 hydrogen together and see how it gets extended. It's going to be symmetrical on each side, and we've bonded these nuclei, which are the positives. Pi bonds, on the other hand, is going to be symbolized by the Greek letter pi, like the one you guys use in math. And this is defined by your textbook as the bonding electrons overlap side by side, and they're most likely found in the sausage region shapes above and below this axis. So here an example of this is a p atomic orbital combining with another p atomic orbital. And they do so where, see, I have my nuclei. These two form an elongated shape above, and then these two form the shape below, and then I have my two nuclei in the middle. How does this actually help with identifying sigma and pi bonds in molecules? Well, we're going to look at a simplified version of this definition to help identify them in the structures that we've been drawing. A sigma bond is a single bond, or it's the first bond in any double or triple. A pi bond is going to be any electron pairs that are found within a double or triple bond that is not classified as a sigma. So if we're looking at this first image right here, this says it has 7 pi bonds because it has 7 single bonds. 1, 2, 3, 4, 5, 6, 7. However, if we look down at this image right here, this one says it has 1 sigma bond, because not only are sigma bonds single, but they are also this first line of a double or triple. So this is my sigma, and that means my other line is going to be my pi bond. If I look over here, this image says that it has 2 sigma and 1 pi. The 2 sigma come from the single bond here, and this one, the first line here, and then my 1 pi bond comes from that second line that I make. And then over here, if I look at propene, I have 8 sigma bonds, 1, 2, 3, 4, 5, 6, 7 single, plus my first line of my double gives me 8. And then I have 1 pi bond, which is that second line of the double. So here we have some examples in your guys' notes. We've already learned how to draw the structures, so I'm just going to go ahead and draw them out for you. If you are still struggling with drawing structures, please come seek my help, because as you guys noticed, you have to have the correct structure in order to get its shape right. And now you have to have the correct structure to tell if something's going to have sigma or pi bonds. So we want to really make sure that you guys understand this for the future. If you guys need to, you guys can pause the video and draw these structures, because I'm going to begin talking about it as soon as we're done drawing. So if you have not got these structures drawn, again, pause this video and then we'll talk about it. Here is HCN. When we're figuring out sigma and pi bonds, we're always focusing on the middle because everything's bonded to the middle. So if we're looking at this middle atom, we have to figure out my sigmas. So remember, sigmas are every original bond you make. So your single and then the first line of your double or triple. So here, this one is said to have 2 sigma from here and then here. And then we have to figure out how many pi bonds. Well, everything remaining will be our pi. So here's my second and third line of my triple would give me 2 pi's. If I'm looking at the next molecule, I have 1, 2, and then this first line will give me 3 sigmas. And then right here, the second line of my double will give me a 1 pi bond. If I'm looking at the third structure, notice that this one's different because I do have a lone pair on the middle. Lone pairs are not a sigma or a pi bond because, note, lone pairs are not bonding anything together. So here, if I'm asking how many sigma bonds, I have 1, 2, 3 sigma bonds or single bonds. And then I have no double or triple, so I have 0 pi bonds. And then the last but not least, I have carbon tetrachloride. I have 1, 2, 3, 4 sigma bonds. And then I don't have a double or triple, so I have 0 pi bonds. That is how we tell the difference between sigma and pi in a structure. If you have questions, please make sure that you guys come ask me. The other type of orbitals that we're going to focus on today is something called hybrid orbitals. This VSEPR theory that we learned in terms of determining molecular shapes is very good at telling the shape, but it doesn't tell me the type of bonds that are forming. So, in what ways is orbital hybridization, which is what we're going to learn about, useful for describing molecules? First, we kind of have to identify what exactly is hybridization. Hybridization is where you take something and you mix it together. It's kind of like my name, Tonda. You combine a Honda car and a Toyota and you get Tonda. Even hybrid cars, note that they run on both electric and gas because they are a mix of two different types of cars. Same thing happens with orbital hybridization. We are mixing together several atomic orbitals to create hybrid orbitals. So an example of a hybrid orbital is an sp. We're combining s and p orbitals. Or sp3d. We've combined sp and d orbitals all into a single hybrid orbital. The whole point of doing this and learning about it is because it provides information about bonding as well as shape now. So let's explain why we have hybridization and what does it actually mean in text of chemistry. And carbon is a very good example to show why we have hybrid orbitals. First, let's look at carbon's electron configuration. Now remember, carbon has 6 total electrons. So that's 6 total electrons, not valence. Our electron configuration is written as 1s2, 2s2, 2p2. That adds up to 6. So if we were going to do the arrows like we did in chapter 5, I have 2, 2, and then if we're following Hund's rule, I have 1 arrow up in each box. This shows I have 1, 2 unpaired electrons. So what we want to do is form a bond with those and pair those up. That means carbon should form 2 bonds. But if you make the structure where carbon bonds to 2 things, this structure is unstable. It doesn't work out. It doesn't like to happen. We know that carbon can actually form, and I'm going to go back to this picture we draw. Carbon in this image formed 1, 2, 3, 4 bonds. How is that possible if I can only draw 2? And the reasoning for that is hybridization. So how does carbon form 4 bonds? And the reason for this, and to explain, is what happens is this S right here, I have one of the S's, and then 1, 2, 3 of the P's combine to form a hybrid called sp3. Notice 1s, 3 P's. And this together, 1, 2, 3, 4, made 4 hybrid orbitals. So 1, 2, 3, 4. This hybridization gives all of these orbitals the same energy. So notice now instead of being on 2 different energy levels, they all have the same energy. So you can put an electron each up in each one of these, and that allows it to make 4 bonds. So this picture shows if carbon has an sp3 hybridization, I can make a bond here. I can make a bond here because I have a lone electron. I can make a bond here and then one here. So I can make 4 sigma bonds. Please note that 1s and 3p orbitals make up an sp3 hybrid. And we're also going to notice that these hybrids also are going to be related to the shape that it has. So here I have a tetrahedral shape. So here in this picture, we're just illustrating the different hybrid orbitals that you're going to see on your homework. An sp hybrid is comprised of one s and one p. Now note I am adding 1 and 1 orbital together, which gives me a total of 2 total orbitals. If I have an sp2, I have 1 s and then 2 p's, so I get an sp2. Notice 1 plus 2 gives me 3 total orbitals that I'm working with. This gives me 3 hybrids. sp3 gives me 1s plus 3p gives me 4 hybrid orbitals that are sp3. This one, notice 1 plus 3 plus 1 gives me a total of 5 hybrid orbitals, which is why things like pf5 can form 5 bonds. And then we also saw in our structures that some things like sf6 can form 6 bonds because it forms hybrids such as sp3d2. 1, 4 plus the 2 gives me 6. Now, if you guys have your electron geography and molecular geography geometry sheet in front of you, one thing I want you to know is on your thing, you often had columns called a bonding group and something called lone pairs. So when you looked at a structure, you told me how many bonding it had, how many lone pairs, and that told you the molecular geometry. Well, we can actually figure out bonding electrons plus my lone pairs actually tells me the electron groups of a structure. And these electron groups correspond to these numbers that I have written out here. If you have two electron groups off that middle atom, you have an sp hybridization. If you have 3 electron groups, you have an sp2, 4 gives me an sp3, and so on and so forth. Now, these electron groups correspond to hybridization. So if you have an sp hybrid, this is going to be your electron geometry. You're going to have a linear shape. If you have an sp2 hybrid, you're going to be trigonal planar. If you have an sp3 hybridization, you're going to be a tetrahedral. If you have an sp3d, you are, I misspelled that, wow. Trigonal bipyramidal. And if you have an sp3d2, you're an octahedron, also called an octahedral. So how do we determine hybridization? First, count our electron groups. I tried to say this on the last slide. Electron groups are bonding and lone pairs. Remember, if you have a double or triple, it counts as a single group. Then hybridization has to equal the number of electron groups you have. So if you have 4 bonding groups, you have 4 electron groups, sp3. That may sound confusing, so let's do these examples. First, let's kind of write these out. We should all know how to draw these, just like I said on the last one. If you are still struggling, please make sure that you come in for help. If I have finished drawing these and you still need to, please pause the video so that I don't lose you when I go to explain how we figure out the answer to what I'm asking. Man, that's a lot of silence. If only I had these drawn out beforehand. Okay. Again, if you are not done, please pause your video so that way you guys are ready. Oops, I need one more electron there for when we're starting. Okay. First, if you pause this video, hopefully you guys have them drawn. Hybridization, we want to focus on the central atom. So I really want to point that out, our central atom. Our first step was to tell me how many bonding groups are on the central. So here's my carbon. I have 1, 2 bonding groups plus I have to look at my lone pairs. Remember, this is on the central, so I have 0 lone pairs on the central, which gives me 2 electron groups total. Then my hybridization must add up to my electron groups. So I have to have an S that gives me one of my electron groups, and then a P will give me my second. So my hybridization is sp. If I look at the next one, let's look at my bonding groups. I have 1, 2, 3 bonding groups on the central, plus no lone pairs, which gives me a total of 3 electron groups. Note my hybridization must add up to these 3 electron groups. So I have an S, and then I have a P, and I can have up to 3 p orbitals, but I only need 2 in order to add up to 3. So 1 plus 2. On the last one, on the next one, if we're looking at the central atom, I have 2 bonding, 1, 2 bonding, plus 1, 2, 3 lone pairs, which gives me 5 electron groups off that central atom. So my hybridization, if I'm looking at this, would be sp3d. 1s plus 3 p's plus 1d adds up to 5 electron groups. Then on the last one, I have 6 bonding plus 0 lone pairs gives me 6 electron groups. My hybridization, let me circle that one, would be sp3d2. Notice 1 plus 3 plus 2 add up to my 6 groups I'm allowed to have. If you have any questions, please make sure you guys ask. And otherwise I hope you guys have a great day.